Good morning to Dr. Arif. We are from Group 3. Today, we would like to present our report on the stability of the floating body. There are 4 members in our group, me as Towan Teng, and the following members are Lok Wei En, Muhammad Elmam, and Chong Chun Fu. This report contains of introduction, theory, working principles, experimental setup, methodology, result, discussion, safety procedure, and the reference. For introduction, the stability of the floating body is a fundamental principle in fluid mechanics, essential for understanding how objects behave when they placed or in the water. This concept is particularly relevant in the fields such as the naval architecture, marine engineering, and environmental science, where the safe design of vessels and structures interacting with water is critical. When an object is submerged or partially submerged in the fluid, it experiences the buoyancy. The buoyancy is a force that counteract gravity and supports the object. The stability of a floating body depends on the relationship between its center of gravity and its center of buoyancy. So the center of buoyancy is a force that outwards, and the force of gravity, which is the weight, is the force that out downwards. When the body is tight, the position of this center determines whether it returns to its original upright position, which is stable, remain in the tight position, which is neutral, or capsize. Capsize is like the overturning, which is unstable. The meta center play a crucial role in this dynamic. It is the point where the buoyant force acts when the body is tight. For a floating body to be stable, the meta center must be above the center of gravity. This relationship is pivotal in designing various marine structures, from the small boats to the large ship, ensuring they can withstand the forces such as the wave, wind, and cargo loads without overturn. For the problem, in this experiment, a rectangular proton floating in the water represents a simple floating body. So the rectangular one is like the proton. The weight of the floating body is assumed to act vertically through the center of gravity of the body. So the weight is the force that acts downwards. A buoyancy force opposes the body weight. So buoyancy force opposes the body weight is the buoyancy force will act upwards, and the weight is downwards. This force acts vertically outwards and is assumed to pass through the center of gravity of the display fluid, which is often referred to as the center of buoyancy. Now consider the proton is tied in the position as the figure 1. The center of buoyancy has moved from B to B pi. So from B to B pi, and here is the angle, the delta here. A line drawn vertically outward through B will intersect the line BG at the point N in the diagram. This is called the meta center. So the B is the B is the center of the buoyancy. Okay, for the figure 2 is the stability of the floating body. So if the floating body is in neutral, the center of gravity and center of buoyancy are in the same position. So if the floating body is stable, the metacentric lie above the center of gravity. The metacenter is the M and the center of gravity is the G. So the metacenter must lie above the center of gravity. So for the floating body to be unstable, the metacenter lies below the center of gravity. So G is the center of gravity and M is the metacenter. So metacenter lie below the center of gravity. There are 3 types of the stability. The first one is the stable equilibrium. The body will return to its original position after being tight. The second one is the neutral. The body will remain in the tight position. And the third one is unstable equilibrium. Means the body will capsize when tight. Capsize is overturning. So this is the terms that we use in this experiment, like M is the mass, G is the gravity, X is the distance by which the horizontal wave is moved, the M is the total mass of the proton, delta is the angle, Gm is the distance between center of gravity and the center of meta, Bm is the distance between body center of buoyancy and center of meta, BG is the distance between the body center of buoyancy and center of gravity. And the I is the second moment, which is inertia. And the L is the length, B is the wave, V is the volume, rho is the density of water, Y is the distance between the base of photon to the center of gravity, and the D is the distance between the base of photon of the to the center of buoyancy. So, objective of this experiment is to determine the height of metacenter by using the tightening method and improve our knowledge of the stability and buoyancy principle in floating body in order to build the safe marine structures and vessels that can bear external force without overturning. This understanding is essential. For the scope, the experiment investigate the stability of various floating bodies in the water, specifically how changing geometry and weight distribution affect their stability. The second one is, it is essential for the naval architecture and marine engineering to comprehend the stability of the floating body. It influences how the boats, ships, and floating construction are designed to stay upright and secure in a variety of situations. Through a series of controlled tilting tests, the effect of buoyancy, center of gravity, and the body shape on the stability of floating object will be examined. The experiment can start with prepare a container with water in for testing. The container is the proton. Then measure and record the dimension and weight of different floating body. Test the stability of the body by touching them and watching how they behave, and modify the weight distribution and conducting further tests to collect the stability data. For the theory we use in this experiment is Archimedes' principle, which is stated in the 6 of the reference. Archimedes' principle is a law of physics fundamental to the fluid dynamics. It states that the upward buoyant force exerted on a body immersed in the fluid, whether wholly or partially submerged, is equal to the weight of the fluid that the body displays. So basically, Archimedes' principle is the upthrust force on a body immersed in fluid is equal to the weight of the fluid display. The second one is the center of gravity. Center of gravity is the theoretical point in the body where the body total weight is thought to be concentrated. So center of gravity basically is the weight of the body. Center of the buoyancy is the center of buoyancy is the centroid of the submerged portion of the body. It represents the point at which the buoyant force acts. The position of the center of buoyancy changes as the body type. Metacenter. Metacenter is a point above the center of buoyancy where the buoyant force acts when the body is tight. The stability of a floating body is determined by the relative position of the center of gravity, center of buoyancy, and metacenter. So, for the body to be stable, the metacenter must lie above the center of gravity. So, if the metacenter and the center of gravity is at the same level, the body is neutrally stable. So, it's neutral. If the metacenter is below the center of gravity, the body is unstable. The working principle. That effect. Different shape influence how the water interact with the body and can change the location of the center of buoyancy and the metacenter, thus affecting the stability. So the first one is different shape, different stability. The second one is buoyancy force. A floating body displays a volume of water while submerged in water. The weight of the water that has been displayed equal to the buoyant force exerted on the body by opposing gravity. This force enables the body to float. So the buoyancy force acts through the center of the centroid of display fluid known as the center of the buoyancy. Analysis of tightings and stability. The center of gravity and center of buoyancy move in relation to each other when the body is tight. Through the center of buoyancy, the buoyant force tries to bring the body back to its upright posture. The body's stability can be inferred from the angle at which its capstan is overturning, return to its initial position, or stay the time. Return to its initial position is the stable one and stay tight is the neutral. So if the metacenter is above the center of gravity, so it's stable, and if the metacenter is below the center of gravity, it's unstable. Weight distribution. Modifying the weight distribution has an impact on where the central gravity is located. In general, stability is increased when the weight is moved lower. The instability may result when the weight is raised. So when the weight is moved lower, stable. When weight is raised, unstable.
Now I will going to present experiment setup of our experiment. In the experiment, the apparatus and the material used in this experiment is thread, carton, cotton bulb, horizontal weight, mass, vertical weight, and also the the water tank for our medium of experiment. And figure 5 show how we set up the apparatus and materials. Next. So the methodology of our experiment is first, initially, we remove the horizontal weight and fix the vertical weight on the top position of the mass. And find the center of gravity by balancing the parton mass on a stabilizer and measure the distance to the CG. And then we put back the horizontal weight to the parton and ensuring it is not tilted, starting at the balanced position. And submerge the parton into the water tank. We place the parton into a water tank and measure the depth of part submerged in the water. After that, we measure the tail of the parton. We move the horizontal weight 10 mm to the right and record the tail angle of the parton. This step is repeated until the parton tail enough for the pump bob to touch the side of the parton, which is a parton wall. And repeat the same step by removing the weight to the left. And after that, we're changing the vertical weight height, and by adjust the height of vertical weight to the middle and bottom positions, and repeat all the steps presented for each new vertical height.
Hi, Assalamualaikum. My name is Muhammad Ilmam and I will be present about the result. So for the first slide, we have result formula. As I explained this before, we have overturning couple C naught equal to mgx for equation 1, and writing couple CR equal to mg gm multiplied by tan theta, which is equation 2. For equilibrium condition, which is C naught equal to CR, then Gm will be equal to small w times x over by capital W times tan theta, will be the equation 3. So for Bm formula, we will equal I over V, I which is equal to LB power of 3 over 12, and V will be equal to W over rho for equation 4. Thus, Gm equal to Bm minus Bg equal to Bm minus Y plus D over 2 for equation 5. And Y is represented by the distance between the base of the pontoon to the center of gravity, millimeter unit. D is equal to depth of the pontoon, which is submerged in the water, and will be the unit will be millimeter, and for the small w will be equal to mass of horizontal weight, kilogram, and capital W will be equal to total mass of pontoon with vertical weight, kilogram. So the next slide is the result. Based on the test 1, we put the pontoon on the top for Y equal to 133 millimeter and D equal to 24 millimeter. So the weight is the small w equal to 0.295 kg, and the capital W is equal to 1.187 kg. And this is the result for movement to the right. The tilt angle is slightly increased by 3 from each x from 10 millimeter, 20 millimeter to the right, 30 millimeter to the right, 40 meter to the right. And movement to the left, which is the same from the right, is starting with the angle of 4.5 degree up to 8.25 degree to 11.25 degree, and 40 for 40 millimeter to the left, it will be 13.5 degree. And in the experiment, we try for the 50 meter to the left and right. The result angle is approaching to the max, and it's not invalid to put in the table. So next, for test 2 in the middle, we put the middle in the middle, which is y equal to 100 millimeter from the base of from the base, and d equal to 24 millimeter. And the movement to the right and left, we increase from 10 to 50, we increase to 10 to 70, which from the starting line a bit small. 10 millimeter to the right is 2.5 degree tilt, angle tilt, and movement to the right and to the left is incredibly close to each other by 0.25 millimeter. And for the 60 millimeter, we got 12.5 degree tilt for both movement to the right and left. And for 70 millimeter to the right and left, we got 14.5 and 14.25 to the left. So the GM calculated here is greater than the test 1. And next, for the test 3, for the last test, which is bottom, the y equal to 77 millimeter and d equal to 24 millimeter, which is the same. Small w equal to 0.295 kilogram and capital W equal to 1 kilogram. So we increase the movement, the length of movement until 80 millimeter. So this is the result we can see. And for 80 millimeter, we got movement to the right with angle tilt of 12.5 degree, and movement to the left is 13 degree. So same relation as before, the GM will be increased than the other test. So that's all. All right.
This is the graph for GM against the angle of tail theta. As the we use the Excel to plot our graph. From the result shown, the y-axis of the graph is GM, which in unit in mm, and the x-axis of the graph is angle of tail in the unit of degree. The result shown the relation between GM and the angle of tail is linear. And from the graph, we get the equation which is y equal to 1.70x plus 18.36x. From the equation we find just now, we substitute 0, and we can get y is equal to 18.36x, which is GM when the theta is 0. Next is the graph of GM against the angle of theta for test 1, movement to the left. The same method we plot the graph, and also we say the same method we get the equation from the graph. The equation now is 1.661x plus 26.19, where the y is GM, x represent the angle theta, and same thing, we substitute 0 and get the GM when respect to theta is 0, which is 26.192. By taking the average of the GM, which is 26.192 plus 80.368 divided by 2, we can approach us to the more accurate GM, which the GM is located at 22.28 for our test 1. When it comes to test 2, also we apply the same way, and this time we get the equation of 0.7296x plus 58.6. Then we also substitute back the 0, and we get the value of GM when respect to angle theta is 0, which is 58.6. And for case of movement to the left, in that for our test 2, the equation of the this graph is 0.4534x plus 60.883, and also substitute the angle 0 inside, and we get 60.883 for our GM value respect to angle is 0. And we take the average GM for our test 2 by taking 58.6, which we get just now from the movement to the right, and plus the 60.883, this value we get from the movement to the left, and divide it by 2, and we get the average value of GM for the test 2, which is 59.7415. Same thing we repeat for the test 3. This time we get the graph with y equal to 0.7132x plus 78.803, and substitute 0 inside to our equation, and we get 78.803 for our GM respect to the angle theta is 0. And then the same way is applied to the test 3 movement to the left. This time we get the equation 1.4055x plus 67.x6, and substitute the angle 0, and also now we get the value of GM 67.x66 when the theta angle is 0, and we average the GM we get just now by taking 78.803 plus 67.x66 divided by 2, and we get the average GM for test 3 is 73.3345.
So the second discussion is calculate the value of the GM for each test using an area of the second moment. Area of second moment is the inertia. Compare and discuss the obtained value with the value of GM from the first question. So the BM is the distance between the body center of buoyancy of the center of matter, is equal to the inertia over volume. So inertia is LB cubed over 12. L is length and the B is the width. And volume is the weight over the density of water. Thus, the GM is equal to the BM minus BG, where the BG is the Y minus D over 2. For test 1, our B is the base is 0.35 meter and H is our height 0.2 meter. Y is our distance between the base of the proton to the center of gravity, and D is the depth of the proton which submerged in the water. So for the inner area of the second moment is BH cube over 12. So substitute the number inside and we can get the answer is 0.0002333 meter. And the volume is the weight over the rho. So the weight we get is the 1.187 kilogram and the rho density of water is the 1000 kilogram per meter cube. So the volume is 0.001187 meter cube. And the BM is the inertia over volume. So inertia is 0.000233 over 0.001187. So the answer we get is 0.1965 meter. And the BG is the Y minus D over 2. Y is 0.133 and the depth is 0.024. So the answer we get is 0.121 meter. The GM is equal to BM minus BG. So BM is 0.1965 meter minus 0.121 meter. So the answer is 75.5 millimeter. So for the test 2, the B is the base is 0.35, H is 0.2, Y is 0.1, and the depth is 0.24. The BH and the depth is the same, so the inertia is unchanged, and the volume is also unchanged, and the BM is also unchanged. And the we change the BG only. So BG is equal to Y minus D over 2. The Y is 0.1, and the depth is also 0.024, and we get 0.088 meter. So GM is equal to the BM minus BG. The BM is 0.1965 minus 0.088 meter. So the answer is 108.5 millimeter. For the test 3, also the same, the base and the height and the depth is unchanged and we change the Y on it. So the inertia is unchanged, the volume is unchanged, the BM is unchanged, and the BG is changed. So this time is the Y is equal to 0.077 minus 0.024 over 2. So the answer is 0.065 meter. GM is equal to BM minus BG. So BM is 0.1965 meter minus 0.065 meter. The answer is 131.5 millimeter.
Okay, so now we compare and discuss the obtained volume with the model of GN from 1. For the test 1, we get the GN for the graph is 22.2 m millimeter. And for the method of area of second moment, we get the GM is 75.5 millimeter. For test 2, the GM is 59.7415 millimeter for the graph and 108.5 millimeter for area of second moment. And for test 3, the GM is 73.3345 millimeter for the graph and 131.5 millimeter from the area of second moment. That's right. So in order to calculate the percentage error, the formula is modulus of experimental volume minus the actual volume divided by the actual volume times the percentage. The percentage error for the test 1, we will get 70.49%. And the percentage error for test 2, we will get 44.95 cents. And the percentage error for test 3 is 44.23%. That's right. And this shows that there is a huge deviation between the experimental volume and the actual volume of GN for each test. This occurs due to some of the error that is occurred during the experiment. The first is the trial type with the pump board is impossible to adjust to 0 tin, which is a systematic error. The issue arises because the equipment is worn out after a few years of operation. Moving the horizontal mesh a little bit is one way to get the thread with the pump board to 0 degrees. However, because the horizontal mesh starting point is now precisely at 0 millimeter, this way it's impossible for us to read the distance of horizontal mesh movement to the left or right. This inaccurate will reduce the accuracy of the experimental volume of GN by contributing a zero error and infusing the volume of S utilized in the GN calculation using equation 3. Next slide. Subsequently, a slight alteration in the surrounding, like the flow of air from the fan or open windows, will cause the water in the tank to readily turn wavy. When we use the ruler to measure the length of the pontoon that is submerged in the water, D, the wavy water movement gets worse because the pontoon was unable to remain motionless when we attempt to measure the volume of the D. The water's movement prevents us from taking an accurate reading. When we take a reading from the ruler, the moving water wave also obstructs our view. The pump board tied with the twig keep and swinging when the water movement is wavy, causing us unable to tell the volume of accuracy. Furthermore, when we measure the volume of T and center of gravity, our eye level are not exactly perpendicular to the ruler reading scale, which leads paralyzed inaccuracy as a result. The real volume of GF will be calculated with less accuracy. Next slide. And the next discussion is discuss the reliance of the meta center on the position of the center of gravity in terms of stability of floating body. In other words, we discuss the reliance of GM and the stability of floating body. A large GM indicates stronger stability as the writing moment is larger and when the body is displaced. However, if GA is too large, it can also lead to stick stability, causing rapid oscillation that might be uncomfortable or even damaging. Conversely, a smaller positive GN resulting in soft stability, when the body has a slower return to the upright position, which can be more comfortable but less stable. Next slide. For this experiment, the meta center on the center of gravity GN for test 1 is 75.5 mm, for test 2 is 108.5 mm, and for test 3 is 131.5 mm. As the vertical wave was shifting from top to the bottom from test 1 to test 3, the GM is increasing and also resulting in increasing of stability of the floating body, which the floating body becomes stiffer in the water. We observe the floating body becomes stiffer when we are doing the experiment.
Right. So for the discussion part, I got the question of discuss the effects of variation in angles of teeth on the position of the meta center. So for the first key point is meta center distance GM and tilt angle theta relationship. As the tilt angle theta increases, the calculated meta center distance GM change accordingly. Generally, an increase in tilt angle appears to cause an increase in the GM values for both movements to the right and to the left. This is evident in the tables test 1 and test 2 and test 3. So next, second main point is the effect of position on GM. Between test 1, test 2 and test 3, the values of GM differ significantly even at similar angles. This indicates that the position height y of the object also affects the metacenter distance. In test 3, which is position lower, y equal to 77 millimeter, GM values are consistently higher than those in test 1, y equal to 133 millimeter, and test 2, y equal to 100 millimeter. This suggests that a lower positioning tends to increase the metacenter distance for the same tilt angles. And discussion part for key point number 3, movement direction impact. The table show values for both movement to the right and movement to the left. Across those tests, the GM values differ slightly between these two directions at the same tilt angle. However, the general trend of increasing GM with increasing theta, the angle tilt, holds in both directions. So for conclusion, the experiment is designed to investigate the stability of the pontoon by analyzing the effects of shifting horizontal and vertical weights. By adjusting the horizontal weight in incremental steps and recording the corresponding angles of tilt, the experiment determined that the pontoons respond to changes in weight distributions. Repeating the test for multiple position of the vertical weight, top, middle, and bottom, allows for an analysis of the impact that the height of the center of gravity, CG, has on the stability. The result likely show that as the center of gravity is lowered by reducing the height of the vertical weight, the pontoon becomes more stable with less tilt observed under the similar horizontal weight adjustments. Conversely, a higher center of gravity results in increased tilt, indicating decreased stability. This suggests that the placement of the weight on a pontoon is crucial for maintaining balance and stability in water-based structure.
Okay, this is the safety procedures. The first one is personal protective equipment PPE. We need to wear the aperture record to show our footing. And the second one is the equipment check. Before starting an experiment, we need to check all equipment, ensure everything is in proper working condition to prevent accident caused by faulty and damaged apparatus. For example, the leaking of water tank may cause electric injury if near the socket. And the third one is emergency equipment and procedures. We need to familiarize ourselves on the location and the operation of safety equipment, such as the fire extinguisher, ice wash session, and first aid kit. Ensure these are easily accessible and in good working order. And we need to have a clear plan for responding to emergency or accident. This is because we are using the field mechanic lab with others also, so we need to clear about the emergency plan also. And the fourth one is we need to have a proper setup. We need to set up the experiment according to the provided guidelines and instrument, and make sure all equipment is securely pressed and properly connected to our procedure. And the last one is training and supervision. We need to conduct the experiment under the lecturing of lab assistant and seek guidance or training if conducting the experiment is first time. Next slide. Okay, this is our reference. The first one is the constructor. We use the first one to find the metacentric height of a floating body. And the second one is we use the second one to find the stability and metacentric height for our floating bodies. And the third one is resource gap. We use this for fluid mechanics experiment 1. Stability of floating body. We use this as reference of our procedure, and the fourth one is stability of bodies a compressive in strike textbook. We use this for our reference also. And the fourth one is metacenter and stability. We use this as our discussion reference. And the sixth one is Archimedes principle. We use this for the theory part. And the seventh one is the stability of floating body as a reference to set out the theory and the experiment. And the last one is so set. Okay, that's all for our presentation. Thank you, Dr. Arif.